Now we are moving on to emission spectra. Emission spectra. So this is one of the most important parts of lesson 1, as I mentioned earlier. After explaining this, we'll take a small break, then after that we'll come back to it again. So emission spectra is a type of spectra, or is a type of detail that can be used to again indicate that electrons are actually arranged in different energy levels within a given atom, right? So this is another piece of evidence that we can use to talk about the fact that electrons within an atom are actually arranged in different energy levels. So before we move directly into hydrogen's emission spectrum, which is the main emission spectrum we are going to be talking about throughout this part of the lesson, we'll learn about what led to this particular emission spectrum we are going to be talking about. So Newton actually discovered that sunlight can be separated into different colors and recombined to form white light. After that point onwards, scientists were somewhat interested in experimenting with this phenomena. So the white light that you currently see around you is not just, now we know white light is type of radiation, and this is not a radiation that is going to consist of only one wavelength. It is basically a number of wavelengths together producing this white light that we see around us. So we can actually see the constituent wavelengths of white light if you send it through a prism, as you can see over here. If you send white light through a prism is capable of expanding the bundle of radiation that is present in white light and giving us a very clear idea about the constituent wavelengths that are found within white light. White light is basically a collection of wavelengths. So we have red, orange, yellow, green, blue, indigo, violet. Basically, students, these are basic colors, but keep in mind we don't actually have a nice red color region and then a nice orange color region, yellow color region broken down like in this diagram. I just wanted to have this diagram and tell you there's not going to be a distinct separation between these colors. It's a spectrum, right? Red color gradually changes to orange, it changes gradually to yellow, so on and so forth. So each of these colors are produced due to, now red color has a range of wavelengths. There is a range of wavelengths that are going to appear red. There's a range of wavelengths that are going to appear orange. Do we have only one type of red color in the entire world, or do we have a spectrum of red colors, meaning there are different shades of red? Yeah, so the answer would be there are different shades of red based on the different wavelengths we observe. Sometimes we can see different types of red color. So anyway, so we can see the white light that we observe is basically consisting of all of these wavelengths. Usually visible light region extends from 400 to 700 nanometers, but in certain texts it is mentioned that it is extending from 390 nanometers to 750 nanometers. So based on the question that you are facing, sometimes they will outline or give you the range of the visible light region. So let's say in this paragraph institute I have included these spectra can be continuous or consist of distinct lines of radiation emitted by substances. Now this is talking about emission spectra. When it comes to emission spectra, students, this is about emission spectra. This is about emission spectra. Now emission spectra can produce two main types of spectrums. One type of spectrum is known as continuous spectrum. The other type of spectrum is known as line spectrum. Now a continuous spectrum is when you have a range of radiation. You have a range of radiation. You have range of radiation where all of the wavelengths are present. For example, if you send white light through let's say a prism, all the wavelengths from let's say 400 nanometers all the way up to 700 nanometers, all of the wavelengths within this range is going to be observed when you send white light through a prism, right? 400, 401, 402, 403 nanometers, 404 nanometers, all the way up to 700 nanometers without missing a single nanometer value. You will have all of the wavelengths present in a when you send visible light through a prism. You will see all of the wavelengths within this region expanded out when you send the visible light through a prism. So this type of spectra are known as continuous spectra. Spectra that contains all of the wavelength values within a given range of wavelength values are known as continuous spectra. Continuous spectra would contain all the wavelengths. But when it comes to emission spectra, majority of the time it will not contain all of the wavelengths within a given range of wavelengths. Imagine when it comes to hydrogen's emission spectra, in the visible light region, you actually see only 4 lines. One line is going to appear red in color, another line is going to appear blue green in color, then blue, and then violet. So only 4 lines are seen in the emission spectrum. So within this particular region of hydrogen's emission spectrum, in the visible light region, you can only see few lines. When there are only a few lines visible to us, or when there are only a few lines within a given range of wavelengths are there, we call it a line spectrum. When you can observe only a few wavelengths within a range of wavelengths, that type of spectra are known as line spectra. It doesn't contain all of the wavelengths, instead it contains only a few of the wavelengths within a given wavelength range. So that is the difference between continuous and line spectra. Continuous and line spectra. So to observe an emission spectrum, you need to energize the material using either thermal energy or other forms of energy such as electrical energy or high voltage electrical discharge, in other words electrical energy. So you have to provide either thermal energy or electrical energy and energize a material, and as a material is energized, it will emit radiation from the material, and this radiation, if you observe their frequencies that are emitted, that is going to be your emission spectra. Now imagine this is a vial filled with hydrogen. I provide this hydrogen vial a lot of energy through electricity, right? Imagine I put 2 electrodes into this glass vial, and inside the glass vial there's hydrogen, and I provide a really high voltage to this glass vial. Then we have now provided energy to hydrogen atoms inside this glass vial, and after absorbing this energy, hydrogen is going to emit radiation. Hydrogen atoms are going to emit radiation. They are going to emit radiation in so many different wavelengths, right? So based on the wavelengths, the frequency also changes, right? So keep in mind, when it comes to electromagnetic radiation, if you know the wavelength, you can calculate the frequency. If you know the frequency, you can calculate the wavelength, right? Because they are all traveling in the speed of light. So I can say that when hydrogen is emitting radiation, it emits radiation in not just a single wavelength, but so many different wavelengths or so many different frequencies. The analysis of the frequencies of the radiation that is emitted by any element is going to be known as emission spectra. The word emission is used because we are analyzing the amount of radiation that is emitted by a material after it was provided with energy. I provided this vial of hydrogen gas energy, and then it started emitting radiation, and analysis of the radiation that is emitted by this particular vial can be referred to as an emission spectra, or range of all of the frequencies taken into a scale can be referred to as emission spectra. Right. For example, a hot iron bar taken from high temperature source emits characteristic glow that represents its visible emission spectrum, while warmth it produces corresponds to infrared region. Another very simple example is that if you take a piece of metal, you heat it up, and if you take it out, you can see the metal is glowing in red. So this red color glow is there due to whatever the visible light it currently emits, and then if you bring your hand close to it, you can actually feel the warmth of this particular object without touching it. That is because it is emitting infrared radiation as well. So if you take it a step further and analyze all of the different types of radiation that is emitted by this particular object, then you're basically constructing a emission spectra for that heated object. Clear? So both sun and heated solids exhibit continuous spectra, that is all wavelengths visible light are present in the spectra, not just visible light, all wavelengths within a given region of radiation is going to be present. But since we are talking about mainly white light here, that's why the visible light word was included in this case. In contrast, emission spectra of atoms in gas phase show bright lines at specific wavelengths within the visible light spectrum. These are known as line spectra, and each element has a very specific line spectra. Scientists use such characteristics lines in chemical analysis to identify unknown atoms, similar to how fingerprints are used to identify individuals. So students, for each element, if you analyze their emission spectra by taking, for example, if you take hydrogen, if you take a gaseous sample of hydrogen, when you provide it with energy, if you analyze the radiation that comes out, you actually have a section of the radiation that falls within the visible light region, and that region is going to be visible to us. You can see when it comes to hydrogen, there are going to be 4 visible lines, and these 4 visible lines, students, are going to be known as hydrogen's emission spectra, or section of hydrogen's emission spectra that is found in the visible light region. And this particular part can be used to identify different elements, because each of the elements will have their own unique pattern. If you observe the emission spectra, each of them will have their own unique pattern. So imagine you have a gas sample of an unknown material. If you want to figure out what element that particular material is, you can analyze its emission spectra. If the emission spectra has, about 6 lines like this in these exact locations, then using the database that we have about emission spectra, we can figure out what element it is. If you have exactly similar lines, this is actually going to be strontium metal, right. So that is how we can actually use emission spectra if you ever want to identify different elements. So yes, they say although the usefulness of this method was recognized in chemical analysis long ago, it was not until the early 20th century the origin of these lines was understood. Figure below shows some lines. So it took us a while to understand why these lines are appearing. Actually, one of the scientists who explained why these lines are appearing is Niels Bohr. Niels Bohr is the main scientist that provided a theoretical explanation to why each element produces these types of different lines as line spectra. And one of the things that I had to mention before moving on into that is that you can see when it comes to emission spectra, the background is black. The background is black. This is black. Why? Because in this region there aren't any wavelengths. So therefore there can't be any light produced there, or there can't be any type of glowing effect, because there aren't any wavelengths within that region. Only when you see these types of different lines, those lines represent different colors or different wavelengths that are going to be found in each of these emission spectra. When it comes to hydrogen, we have mainly 4 lines. We have a red color line, we have blue-green color line, we have a blue color line, and a violet color line. So each of these lines are produced due to the radiation that hydrogen emitted that has that particular wavelength. You can see red color light was produced at a very specific wavelength value. And then again blue, green, blue and violet lights are again going to be produced at very specific wavelength values, and the other regions do not carry any wavelengths. That is why they are black in color. The visible region of hydrogen's emission spectra can be observed this way as well. If you take a vial that contains hydrogen provided with a high voltage, we can see the hydrogen starts to glow, right. Actually hydrogen glows in this color, very nice color. Take a look at the board now. Take a look at the board, right. So now you can very clearly see that hydrogen is going to be having a light purple pink color. So if you send the light that is produced, now observe here, if you send this light that is produced through a small slit, basically this particular opaque object is there to stop all the other radiation or all of the light coming all throughout this region, because we want to only take a small beam of light. So we can see there is a opaque board here with a small slit cut out in the middle, which will take just a beam of light. We will send this beam of light through a prism, and the prism will separate the constituent wavelengths within this beam of light very clearly and give us this line spectra. Okay, the prism's job is to separate the radiation into its constituent wavelengths. Now this pink color light is consisting of 4 different wavelengths: a red color wavelength, a blue-green color wavelength, blue color wavelength and a violet color wavelength. So you can see they have very specific wavelength values. If this is the nanometer scale indicating the wavelength of each of these radiation that is produced. You can see different colored lines have very specific wavelengths, and the remainder is going to appear black. In this case, they have not mentioned that over here clearly, but you can see the actual spectra is going to appear black, the background appear black, but the main lines appear colored. Right, so now we are going to be moving on to a small explanation about hydrogen's emission spectrum. We observed how hydrogen's emission spectrum was produced. Now we are going to be moving on to a small explanation about hydrogen's emission spectrum. Before we do that, I'm going to take a small break, students. We'll take the usual 15-minute break that we always take. And before I go there, if you have any questions, you can bring it to me, because once we start the class, we can start fresh and discuss what is the main reason why we observe an emission spectra of any element. So before I go for the break, if you have any questions to ask me, please do so that we can discuss it before I leave. No questions? All right, everyone. Then in that case, I will take a small break. We will meet again after 15 minutes. That. All right, everyone. Now we can start having a look at hydrogen's emission spectrum. Now we are going to learn how exactly the hydrogen's emission spectrum is produced. So when we are talking about an emission spectrum, we learned that emission spectrum can be produced by first energizing the sample and then observing the radiation that is emitted by the sample. So that is how we obtain hydrogen's emission spectrum as well. So our main interest is in figuring out how these emissions are actually produced. So to explain this, a scientist known as Niels Bohr provided a theoretical explanation. He said around each atom's nucleus there are energy levels, or he called them aloved orbits. Aloved orbits where electrons are going to be present. Right? So around each of the nuclei of each atom, electrons are arranged only in these aloved orbits. If you have the nucleus, there's going to be the first aloved orbit close to the nucleus, and then a little bit further away from the nucleus there's going to be another aloved orbit, like we can see over here in this image. So aloved orbits are going to be having different diameters and they are going to obviously have different energies. Actually, as you move further away from the nucleus, the energy of the orbit or energy level is going to be greater, right? So the first energy level that is closest to the nucleus is going to have electrons that are lower in energy. Okay, so when electron is strongly attracted to the nucleus, the electron has very low amount of energy. Now compare that to a free electron. Now free electrons are not attracted to anything. They can move however they like, they have a high amount of energy, but their energy is going to be limited the moment they are attracted to a nucleus. The moment the electron is pulled to a nucleus and kept around the nucleus, the electron's energy is going to be limited or smaller compared to a free electron, right? You can also think about like certain examples to remember these things if you like. For example, when the teacher is not in the classroom, you guys are free, right? You all are doing all sorts of things, right? But as soon as the teacher comes and you have to pay attention to the lesson, you all are going to be a bit more stable, but bit more limited in your energy as well. You can't display the energy you have, jumping here and there, doing the things that you usually do when the teacher is not there in class. You can't do the same things when the teacher is present, right? So when you are free, you have more energy. And when you are, let's say, bound to a nucleus, or when your teacher is present, like I told, you don't have that much energy, or you don't display the amount of energy you have, we can say that state is a lower energy state, which is more stable. Similarly, electrons are also going to have a limited amount of energy when they are attracted to a nucleus. Okay, and in chemistry, students, the lower the amount of energy they have, or any electron has, the more stable it will be. The higher the amount of energy an electron has, the less stable it's going to be. So that's something to keep in mind. So if you take a nucleus, around the nucleus there are going to be allowed orbits, or in other words, allowed energy levels. In O levels you would have named these energy levels K, L, M, N and so on. But now we are going to be mainly addressing them by their energy level number, or we can call them principal quantum number. We'll be learning about quantum numbers after this. So we usually call these energy levels energy level 1, or n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. Or instead you can call them energy level 1, energy level 2, energy level 3, energy level 4, so on and so forth. So students, the energy levels closer to the nucleus have a lower amount of energy. As you move further away from the nucleus, those energy levels will have a higher amount of energy. Same example, classroom setup. The front benchers are less likely to misbehave, and they are less likely to do anything other than focusing on the lesson. They appear to be very calm. But as you move towards the back bench, right, you can see the people in the back bench are usually high in energy, right? They are talking all the time, sometimes eating, doing all these types of more distracted activities, right? So they are higher in energy and more distracted. They are less calm, indicating more unstable nature. So similarly, when you're talking about energy levels that are closer to the nucleus, they are going to be strongly attracted to the nucleus, or the electrons in those energy levels are going to be strongly attracted to the nucleus. So therefore, energy of these energy levels, or electrons that are in these energy levels, will have a small amount of energy and therefore will be more stable. And as you move away from this nucleus, the energy levels that are further away from the nucleus usually house electrons that are higher in energy and has a loose connection, or not loose connection, sorry, and has a lower attraction to the nucleus, right? So that is something that you need to keep in mind. And electrons can actually, if provided the right amount of energy, can move from their original energy level to a higher energy level, and that is done mainly by absorbing energy. So let me show this to you like this. If you talk about hydrogen's first electron, right, imagine this is the nucleus of the hydrogen. You have first energy level of hydrogen here, and then we have second energy level, third energy level, fourth energy level, so on and so forth. There are infinite number of energy levels. Over here, when it comes to hydrogen, we have the first electron here, and I told you each energy level will have their own type of energy, but first energy level has the lowest amount of energy, and then second energy level has more amount of energy than the first one, and third one will have more energy than the second, so on and so forth. Energy is increasing as you move away from the nucleus. As you move away from the nucleus, energy of the energy levels will increase. If this electron that is present over here can absorb, if this electron can absorb energy that is equivalent to the energy gap between these energy levels, between the first energy level and the second energy level, there's an energy gap. If you can absorb that particular energy gap, the electron will go from the first energy level to the second energy level. So now this electron has higher amount of energy than before. We say that the electron is excited. Electron was usually present in, when it comes to hydrogen's electron, it is usually present in the first energy level, and that is the usual energy level the electron is present in when it comes to hydrogen, and that particular energy of the hydrogen's electron is usually referred to as the ground state energy of the electron. So what is the ground state? When an electron is present in its usual energy level, that electron is said to be in its ground state. Right now you and I are in a ground state. Basically, again, another analogy. Do you see me excited over here like it's my birthday today? Not really. That is because this is a usual day for you and I. I'm teaching and you are a student, you are learning. So a usual day in your life is somewhat common or somewhat similar to an electron's ground state. So an electron's ground state is defined as the state in which the electron is going to be present in with its lowest state of energy in an atom. So when you arrange an electron in an atom by providing it the lowest possible energy state, that particular state of that electron is known as the ground state, right? So an electron that is in the ground state is quite stable because that is the lowest possible energy state that that particular electron can be present in. So ground state of an electron is one of the most stable states that it can be in. And when you provide it with energy, if it absorbs energy and moves into a higher energy level, keep in mind it can only absorb the correct energy value. For example, if the energy gap between these two is 15 let's say kilojoules per mole, I know that's a large value, but for this particular example, let's take that value, 15 kilojoules per mole energy gap is there, let's say, between the first and second energy level. If this electron absorbs 15 kilojoules of energy only, it will be able to move on to the second energy level. It can't absorb any less and move on to the second energy level. It can't absorb more and move on to the second energy level as well. It can absorb exactly 15 kilojoules of energy and move on to the second energy level. And now this electron is at a higher energy state. Earlier it was at ground state. Now it is at a higher energy state. So we call this an excited state. Now excited state definition is when an electron has absorbed energy and has moved into a higher energy state than its ground state, temporarily it is known to be in a excited state. So few things. Excited state is temporary. To reach there you need to absorb energy and move out of the ground state. So the high energy state is going to have more energy than the ground state. And like I mentioned earlier, sorry, this is the second time I'm mentioning it, it is a very temporary stage because the excited state is going to be unstable. So when the electron absorbs energy and moves into a high energy level, it is said to be in an excited state, and the excited state, due to its high energy nature, is unstable. It has to come down to the ground state. So when the electron returns to the ground state, students, we'll draw it in a different color. When the electron returns to the ground state, the energy difference between these two energy values should be released, right? You can't carry that energy and return to the ground state. You can't do that. You have to release that energy and return to the ground state. If you release that energy only, you will be able to return to the ground state, right? So when this energy is released, or a better word for release would be emitted, right? When the energy in the high energy state is emitted and released, returned to the ground state, the emitted energy is released in the form of electromagnetic radiation, right? So this energy that is emitted is going to be present in the form of electromagnetic radiation, which means it has a frequency and a wavelength, right? You can say that it is removed as a photon. So these energies are going to have a very specific frequency or a very specific wavelength. If you know the frequency, you can calculate the wavelength, right? So this is the reason why the emission spectra is produced. When we provide electrons, they absorb energy and move into higher energy levels. Staying there is not possible, right? Because it is, you can't stay there forever. It's a temporary state, unstable. So excited state is not a permanent state. So it has to come back down to the ground state. As it comes back down to the ground state, the energy difference is released as radiation. And as you know, the radiation will have, if it is released as electromagnetic radiation, it is going to have a very specific frequency value and a very specific wavelength value. So we can draw an emission spectrum using the frequencies of the emitted radiation, or we can draw an emission spectrum using the wavelengths of the radiation that is emitted. We actually have drawn them using both, right? So another very important thing to learn is this. So let me draw this for you. Bear with me a second. So instead of drawing it just like in an atom, I'm going to be drawing this energy levels like this, okay? Now there is a reason why I have drawn these energy levels this way. I will explain to you in a second. So imagine that this is energy level 1, this is energy level 2, this is energy level 3, energy level 4, and we have energy level 5 drawn here. So students, the usual electron in hydrogen's atom is found in the very first energy level. This is where the electron is going to be found. But if we provide electrons energy to the electron, electron can absorb energy and can move from the ground state or this particular energy level, and it can move to a higher energy level. Now in purple I'm going to show you the excited electrons or the excited states of that particular electron. It can move, let's say, to the second energy level, or sometimes it can also move all the way to a higher energy level, like let's say to the fifth energy level. It depends on the amount of energy that it absorbs. It can move sometimes to the second energy level, or sometimes to the third, fourth, fifth. There are infinite number of energy levels, all the way to the infinite energy level it can get excited. But it all depends on the amount of energy that it absorbs. Now we are providing high voltage, so we are providing all sorts of energy, right? So it can absorb relevant amount of energy to move from the first energy level all the way to even the infinite energy level. And then bear with me a second, there was an electron here, and then it has to come back down. It has to come back down to the ground state. So when it's coming back down, it will release the amount of energy that it absorbed as electromagnetic radiation with a very specific amount of energy. So I will say E1 is the energy. So therefore they will have a very specific frequency value as well. That's what I have indicated by over here nu1. Nu stands for frequency, right? So it has released the energy difference between these two energy levels as electromagnetic radiation with a very specific frequency value. And these higher electrons that are present in way up high, in higher energy levels, they can sometimes fall back down step by step, meaning from the 5th energy level they might fall back down to 4th, and then to 3rd, then to 2nd, and then to 1st. Right? They can fall back down step by step, or else they can fall back down randomly, like from the 5th all of a sudden to the 3rd, and all of a sudden to the 1st. Or from the 5th itself it can directly fall down to the 1st. So it's all up to chance. You can't expect a specific way in which the electron should be coming down. For example, if you roll down a marble, in a staircase, you won't necessarily know how it's going to be falling down. It might sometimes fall one step at a time, or sometimes it might bounce over one step and skip about 2-3 steps and move on to the next step. So it all depends how the energy transition is going to happen, how the electron transition is going to happen, whether it's going to come down from the 5th energy level directly to the 1st, or whether it's going to come down to the 4th, then to the 3rd, then to the 2nd, and then to the 1st, or whether it's randomly going to come down from 5th to the 3rd, and then 3rd to the 1st, or maybe 5th to the 4th, and then 4th to the 1st. Who knows? So it's all up to probability. However, the absorbed amount of energy, for example, imagine you had a ball here. Think about the potential energy. If you had to bring this ball all the way up over here, and then if you allow it to come down to the bottom again, the energy, the potential energy that you stored over here in the ball when you took it up is completely released when you bring it down all the way to the bottom again, right? So similarly, if you give a ground state electron a specific amount of energy, the amount of energy that it has taken and gone up will completely be released as it comes back down to the ground state. It might be released in 1 step, 2 steps, 3 steps, depending on how the electron actually falls back down to the first energy level. It might release in maybe 1 step or multitude of steps. Okay students, it's very important to remember that. So it's not just a single fall that could happen, right? And keep in mind, you can't actually have electrons fall in between energy levels. That is what this is indicating. You have to make sure that the electron is falling directly to an energy level. It doesn't stay between energy levels. For example, electron won't stay here. This is between energy levels. This is not possible. So it might, just to show you, it might fall down to the second energy level and then to this energy level. So imagine the energy gap between the 5th and the second energy level is different, right, to the energy gap between the second and the first. So I will say energy release is E2 is equal to h nu 2, and energy gap between the second and the first was already given here. So when the electron transition from the second to the first energy level, the energy release is still going to be the same, E1. This is also E1. E1 is equal to h nu 1. Or else the electron could fall all the way from the 5th energy level down to the first energy level by releasing a different type of energy, in the sense not E1 or E2, let's say a large amount of energy, E3. So that can be represented by h nu 3, right? So when electron falls from the fifth energy level to the first energy level, the energy gap is massive, right? So therefore huge amount of energy is released. So that's why E3 is going to be having a higher amount of energy in it, and therefore frequency is also going to be higher when it comes to this particular example. In nu 3 the frequency is higher. Okay students, so these radiation that is emitted, as you can observe, can have different frequencies, and this is just for a single electron in a single hydrogen atom. But you know, in a sample of hydrogen there are so many different hydrogen atoms that can have all sorts of electron transitions, sometimes moving electrons from first energy level to the second, second to the third, or maybe first to the sixth, and sixth to again back to the third. So many different types of electron transitions can happen in a large number of hydrogen atoms. So at that point they can end up releasing a large number of different radiation which has different frequencies. So that is what actually gives rise to our hydrogen's emission spectrum. Okay students, that is something again I wanted you to know before moving on to the next part. So at this stage, do any of you have any questions to ask me? Do any of you have any questions to ask me? Anyone? Tell me. Do any of you have any questions, students? All good? Everyone, I want this to be an interactive session, so please do respond. Can an electron in energy level, right, can electron in energy level or a free electron absorb a photon? Give me a second. Can an electron in an energy level or a free electron can absorb photons? Free electrons are anyway capable of absorbing energy, so that's not a problem. So when you have a bunch of free electrons, if you provide them with energy, they will be able to absorb energy. But in this case we are talking about electrons that are found within the atom. So these electrons are not free. When you are talking about emission spectrum of hydrogen, the electrons we are talking about, or basically we are talking about hydrogen atoms. So within the hydrogen atom you don't have any free electrons. Within the hydrogen atom, whatever the electrons that are found are not free. Those electrons are bound to the hydrogen atom. So we only talk about the electrons that are found within an atom. So in this case we don't talk about free electrons absorbing energy. All the energy we spoke about over here was absorbed by electrons that are found within an atom. Okay, so and when they absorb energy, they have to make sure that they absorb energy that is equivalent to the energy gap between two energy levels. They have to absorb energy that is equivalent to the energy gap. For example, this particular electron, when it wants to jump to the fifth energy level, there is always an energy gap between the first and the fifth energy level. The fifth energy level has high amount of energy in it compared to the first energy level. So that very specific energy gap should be absorbed by these electrons. Right, I meant in two separate cases. Yes, free electrons, like for example in another example, free electrons, yes, can absorb energy. In this example we were only talking about, that's what I said. So yes, I hope now it's clear. Right, very good. Okay, so please bring in your questions like that. That is good. Now students, we move on to electron transitions. Now so we can see over here, this is another diagram which we can see electrons can jump from first energy level all the way to high energy levels. and then sometimes when they fall, they can directly fall. Like I told you, there are so many ways in which they can fall back to the first energy level. This very first part of our diagram, we can see electrons are falling from higher energy levels. This indicates electrons falling, or we can say electrons are transitioning from higher energy levels all the way down to the first energy level. And this axis is talking about energy. So you can see the first energy level has a very low amount of energy, and the higher energy levels have a high amount of energy. And these arrows that are pointing downwards, their lengths actually can be taken as an indication of the amount of energy that is released when the electrons are falling down. The longer the arrow, the more amount of energy that is actually released, right? Because you can see from the first energy level, and over here we have the 7th energy level, you can see one electron falls all the way from the 7th energy level down to the first energy level. 7th energy level has a really high amount of energy, and the first energy level has low amount of energy. So that energy level is huge. So when electrons are falling, energy gap is huge. So when electrons are falling from 7th to the 6th, a huge amount of energy is released. But when electrons are falling from the 6th to the first, a slightly less amount of energy is released, not extremely less, slightly less amount of energy is released, because 6th energy level has low amount of energy than the 7th energy level. So when it is falling from the 6th energy level to the first energy level, slightly less amount of energy is released. And you can see so on and so forth. You can see when it comes to this particular final one that I'm going to point at here, when electrons transition from the 2nd energy level to the first energy level, again considerable amount of energy is released, but compared to all of the other energies that are released in this particular series, it's going to have the lowest amount of energy is released. So you can see in this diagram we talk about how electrons are transitioning from high energy levels to different energy levels. Now I told you electrons are capable of coming down sometimes directly from high energy level to the first energy level, or sometimes they fall randomly to different energy levels and finally to the first energy level. So based on how electrons are falling down again to the first energy level, we can categorize them into few different series. We can call them Lyman, Balmer, Paschen, Brackett and Pfund series. Lyman series talks to us about all the electron transitions that are happening from higher energy levels all the way down to the first energy level. If electrons are directly falling from high energy levels directly to the first energy level, the radiation that is emitted due to these types of electron transitions are falling under a type of an area of hydrogen's emission spectrum known as Lyman series. And when electrons are falling from high energy levels to the 2nd energy level, those types of electron transitions produce a section in the hydrogen's emission spectrum known as Balmer series. Now these electron transitions are actually going to produce, some of these electron transitions are going to produce radiation that falls within the visible light region, right? 750 or 390 to 750 nanometer range. So therefore this radiation has colors. That's why some of these arrows are colored. And then we have Paschen series, is basically a series in hydrogen's emission spectrum that is produced when electrons transition from high energy levels to the 3rd energy level. Brackett is when electron transition from high energy levels to the 4th energy levels. And Pfund, there's another series called Pfund. That particular series is produced when electrons transition from high energy levels to the 5th energy level. So there are few different series that are going to be discussed in this lesson today. I just want you to know first of all that each of these series are produced when electrons are transitioning from high energy levels to different energy levels. Lyman series when electrons fall from or transition from high energy levels to first energy level. Balmer when electrons fall from high energy level to second, and then we have Paschen, high energy level to the third, Brackett, high energy level to the fourth, and Fund, high energy level to the fifth. And students, doesn't, just because I have drawn the arrows over here and stopped, doesn't mean the electrons stop here. Of course, electrons somehow will come to the ground state, meaning the electrons that are over here again will come back down. But that particular line belongs to which series? Lyman series. That's why we didn't write it right under Balmer, just so that we can very clearly see what we're talking about. Right? The electron transition from second to the first comes under Lyman series. That's why it is not drawn here. That doesn't mean electrons stopped right after falling to the second energy level. This doesn't mean when electrons fall into the third energy level in Paschen series, the electrons stopped there. They again somehow came back down to the first energy level. But it would have sometimes happened in this manner, right? Paschen to, the third energy level to the second energy level, and second energy level to the first. Or from third energy level itself, it would have fallen into the first energy level. So many options are there, but when it comes to very clearly identifying different series, we don't actually draw all of them right next to other series. You have to understand, when you talk about Balmer series, we are not talking about electrons falling from high energy levels to second energy levels and staying there. Electrons don't stay there. We talk about only electrons falling from high energy levels to a second energy level related energy transitions. That's it. We don't talk about the fact that electrons are staying here or not, because we obviously know electrons have to return to the ground state. Right. So up to this point, is everything clear? Up to this point, is everything clear? Everyone, yeah? Right. I have Dinadu confirming yes. Thank you. I think that was another student, I'm sorry, confirmed. All right. All right, brilliant. Thank you. So now, students, this is the image that I directly took from your textbook. Now, in your textbook, if you go through it, you would notice that they give you this image and they give you these energy values in kilojoules per mole, right? And some students actually find it very difficult to understand, because these are all negative energy values, and the negative value decreases as you go up. And we learned, as we go up, or as we go away from the nucleus, the energy of each energy level is increasing. That's what we learned. But in the textbook, we have been given these very weird energy values here. So what is the explanation to this? Now, students, whatever that we have discussed so far still remains true. We said, when it comes to energy levels that are closest to the nucleus have a lower amount of energy, and as you move away from the nucleus, energy levels will have a higher amount of energy. That is something that we discussed earlier. What they are discussing over here is the same, but they have given energy values. There is a way in which we can calculate the energy of each energy level using a constant known as Rydberg's constant. And that is additional knowledge for you, but I will give you that additional knowledge next week if we have the time to talk about how energies of different energy levels are calculated. It is not within this syllabus, but if you really want to know why these negative values are there, that is because we use a particular equation to calculate the energies of each different energy level. And by a convention, we have agreed to use a negative sign in front of each of these to indicate the fact that compared to a free electron, that an electron found in an atom will always have lower amount of energy, right? Compared to a free electron, electrons found within an atom will always have low amount of energy. So that is why we have all of these energy values in negative values, right? Compared to a free electron, electrons found in the very first energy level, that is the closest to the nucleus, have 1312 kilojoules per mole lower amount of energy, right? Extremely low, 1312 kilojoules lower amount of energy compared to free electrons. So these are not just kilojoules, kilojoules per mole is the unit. So compared to free electrons that are outside of the atom, this is the edge of the atom, outside of the atom, compared to free electrons, electrons that are closest to the nucleus are found in the first energy level, and energy level 1 can hold electrons that have 1312 kilojoules less amount of energy compared to a free electron. So meaning that has the lowest energy electrons. First energy level holds the lowest energy electrons. And then you can see the second energy level holds only 328 kilojoules per mole low amount of energy compared to free electrons. So obviously this particular energy level holds electrons that have high amount of energy, right? If the energy of the first energy level electrons is 1312 less than a free electron, and this only 328 kilojoules less, which has high energy electrons between these two energy levels. This one, right? This one definitely has electrons that have a high amount of energy. That's why the negative sign or negative value of the energy of that particular energy level is smaller. You can see negative values become even smaller and smaller as you move away from the nucleus, indicating that these energy levels are increasing in energy. And at the infinite energy level, you can see it becomes 0, indicating electrons that are in the infinite energy level has similar energies or close to similar energies to free electrons, meaning they have the highest amount of energy within an atom. So is this clear, students? Is this clear? Because this particular diagram is something that a lot of students find difficult to understand in the textbook. Sometimes they call and ask also. So is this clear? Yeah? Right. Do you have any questions? Now do let me know if it is not clear, students. I need to know before I move forward. All right. Okay, there are a few who are clear with it, but if you have any questions, let me know. The only reason I brought this up is just to explain point 1, which is why the negative values are there, and then to explain a very important second point, which is observing the energy gaps. You can see these are all calculated values. You can see between the first and the second energy level, the energy gap is the largest. Energy gap is the largest. Between these two, you can very clearly see the energy gap is close to 1000, not exactly 1000, close to 1000 kilojoules per mole. Between these two, we can say it is somewhat close to 160, right? Rough figures. And then actually 100, not 60, 100, we have 46 and 28 here, close to 180. Okay, and then between these two, the energy gap is you have around 64, and then they haven't given any details below that. So you can see, if you observe here, bear with me a second, I need to write the 180 clearly. 180, let's say this is 64, right? We can see as you move away from the nucleus, very clearly energy of each individual energy level is increasing, but the energy gaps between energy levels is decreasing drastically. Energy gap between energy levels is decreasing drastically. Do you see this type of very large energy gap anywhere else? You can see when you move further away, energy gaps are becoming even smaller and smaller. Right? This energy gap is almost 1000 kilojoules, and this one is not even 200, and the next one is 64. Right? So it is becoming even smaller and smaller. So therefore, this energy gap is going to be the largest energy gap between two energy levels within the atom, for any atom, that is. So all the atoms won't have the same energy values, but when it comes to atoms, energy difference between the first and the second energy level is going to be the largest. Energy difference between the first and second energy level is going to be the largest energy difference between energy levels. So this energy difference is so significantly large. When electron falls from the second energy level to the first energy level, the produced electromagnetic radiation has a wavelength that falls within the UV region. UV region is a high energy region, right? So when it comes to electromagnetic spectrum, we learned as the frequency increases, obviously, as we know, E energy is equal to h nu. H is a constant, Planck's constant. So therefore, energy is proportional to frequency. As energy increases, frequency increases, or as frequency increases, energy increases. So if there is a huge amount of energy released when electron is falling from the second energy level to the first, then the frequency of that is also really, really high. Frequency high meaning wavelength is going to be what? If the frequency is really high, what can you tell about a wavelength? We know this. And when it comes to electromagnetic radiation, c is going to be the speed of light for any electromagnetic radiation. So therefore, wavelength is going to be equal to c divided by nu. C is a constant. So therefore, we can say wavelength is indirectly proportional to frequency. So if the frequency is increasing, wavelength is decreasing. Okay, students. So you can actually talk about the frequency of the radiation that is emitted and the wavelength of the radiation that is emitted using this knowledge. And you can see, since there's a huge energy gap, the energy released when it comes to this Lyman series, all of them actually release energy in the UV region. All of them release energy in the UV region. When it comes to Balmer series, it releases energy, the first 4 lines in visible region, and there's a high energy electron transition that is going to have energy released in UV region. All the others release energy in IR. Okay, so that is something to keep in mind. And now I want to move on to the spectrums that are formed here. So students, there are few different types, actually 2 main types of spectrum that you see in your textbook as well. That is, the very first one is the most commonly used one when it comes to our discussions, questions. We use this particular hydrogen's emission spectrum. Hydrogen's emission spectrum, just to recap before we take a look at this again, is produced by providing energy to a sample of hydrogen and energizing the hydrogen. And at that point, students, hydrogen will absorb the energy and excite electrons to high energy levels. As electrons fall into the ground state again, it will release radiation or electromagnetic radiation. And this electromagnetic radiation released based on what kind of electron transitions took place will release different amounts of energy, and these different amounts of energy will have different frequencies. And if you take a look at all of those frequencies and draw them in a scale like this, you're going to get a graph like this, which we now call hydrogen's emission spectrum. You can see there are few lines between 0 and 0.5 here, and this is actually a frequency, and frequency is taken as 10 to the power 15 per second or hertz. So basically whatever the values that are here should be multiplied by 10 to the power 15. So there's towards the right hand side we have larger frequencies, towards the left hand side we have smaller frequencies. You can see there are few lines indicated here, and then again this indicates that this is a single series, which is Parsons series. So Parsons series related frequency values. Parsons series is produced according to what we learned when electrons transition from high energy levels to the third energy level. So when electrons fall from different high energy levels, for example from fourth energy level to the third, fifth energy level to the third, sixth energy level to the third, they release different amounts of energy, and frequencies related to those energies are found here in this region, and then frequencies related to the Balmer series are found here, and the frequencies related to the Lyman series are found here. So this is hydrogen's emission spectrum drawn as a frequency distribution, meaning we have taken the frequencies of each of the radiation that we see when we provide energy to hydrogen and observe their emissions. If you draw a frequency distribution of hydrogen's emission spectrum, this is what you're going to get. And then over here we have hydrogen's emission spectrum again once more, but this is a wavelength distribution of hydrogen's emission spectrum. So if you know the frequency of a radiation, you can calculate the wavelength also, right? So we can draw a graph using wavelengths also. That is what we have done here. We usually mainly use frequency distribution, but you have to know about this as well. You can see if you compare the both of them, it's going to be somewhat different to one another. Now one of the key observations that you should make when it comes to frequency distributions and wavelength distributions, that the lines of each series gets closer and closer together as you move towards higher frequency values. So the frequency is increasing in this direction. You can very clearly observe that using a very important point, or this is something that you should keep in mind when it comes to any series. If the lines or the gaps between the lines are becoming smaller and smaller, in that direction frequency is increasing. You can see Balmer also, we have a larger gap here, then a smaller gap, again another smaller gap than the previous one. So gaps between lines are decreasing towards the side where the frequency is increasing. So according to this particular diagram, to which side the frequency is increasing, we can say frequency is increasing to the right hand side. Now we don't need to make that kind of assumption because the frequency scale is given here, but imagine there was a question where you are given a series like this. Imagine there was a question where you are given a series like this. Bear with me, I don't like this color. We'll change the color a bit. Right. If you are given a series like this one, right, if you are given series like this one, and if you are asked in which direction is frequency increasing, you can see the gaps between the lines are decreasing as you go to the right hand side. So the frequency is increasing as you go to the right hand side. And if they ask to which direction is the wavelength increasing, You need to remember frequency and the wavelength are inversely proportional. Frequency and wavelength are inversely proportional. If to this side frequency is increasing, to which side is wavelength increasing? Is it increasing to this side? No, the wavelength should be increasing then to the other side. Wavelength is increasing to the other side because they are inversely proportional to one another. Okay, so one observation is that as you move towards higher frequency areas, the gaps between the lines decrease. So over here, and sorry, another very important observation to make over here is this. You can see here, Lyman series is quite a broad series when you draw it in the frequency distribution, and Paschen is a very narrow series here, right? Because this is a frequency distribution that we have drawn. Lyman has really high amount of energy, and you can see Lyman is present in the higher frequency area of the frequency distribution, and it has a broader series, or the line series is broader when it comes to Lyman drawn as a frequency distribution. But when you observe the Lyman series as a wavelength distribution, when you talk about the wavelength distribution of hydrogen's emission spectrum, Lyman series is going to appear very small. Paschen series on the other hand appears quite large, right? So these are differences, but even in this particular drawing, still the statement I made about where the frequency is increasing remains true. When you are observing the gaps between lines, to the direction where the gaps between lines are decreasing, the frequency is increasing. If you take Paschen series, you can see the gaps are decreasing towards the left hand side. So in this direction, frequencies are increasing, right? Balmer also very clearly you can see gaps between lines are decreasing towards the gaps between lines are decreasing towards the left hand side. So that means what? Frequency is increasing towards the left hand side. I hope that is clear to all of you. Right. So now we have a comparison between the two over here. Okay, so you can very clearly see them side by side, and you can see this is having gaps between lines decreasing towards the right hand side, this is having gaps between the lines decreasing towards the left hand side. And as a frequency distribution, Lyman series is broader, but when you talk about the wavelength distribution of hydrogen's emission spectrum, Lyman series is narrower, basically somewhat opposite to the frequency distribution of the hydrogen emission spectrum. So hydrogen's emission spectrum can be drawn as a frequency distribution or as a wavelength distribution, but majority of the time we prefer to use the frequency distribution, because then we can easily talk about energy of each of these lines because of this relationship, and we know as the frequency increases, energy increases. So this is a more straightforward, easy relationship between frequency and energy. So therefore we can talk about how the energy gap is going to be proportional to frequency gap, and we can see how we are going to be using that in the future as well. So in the next class we will talk about that in detail. So students, this is basically the intro to our emission spectrum. Today we couldn't finish all of the details, or I couldn't give you all of the details about hydrogen's emission spectrum. Obviously this is something that will take more time for us to discuss and complete. There is a separate note that we have to take under hydrogen's emission spectrum as well. So I hope by now the basic concept about hydrogen's emission spectrum is clear to you. The basic concept is this. We take any element in gaseous form, or if you take hydrogen, hydrogen is going to be present as hydrogen molecules. We can take it into a glass vial, and we can provide these hydrogen molecules with electrical energy. So when we provide the energy, one of the first things that happen is hydrogen molecules actually break down into hydrogen atoms, right? Hydrogen molecules will turn into hydrogen atoms. They will break and form hydrogen atoms, and these hydrogen atoms can absorb energy or take up energy, and the electron in the hydrogen atom can move from the ground state to a high energy level, which we now know to be known as excited state. And then electrons in the excited states can come down to the ground state in many ways. And as they come down to the ground state in many ways, the energy gap between each of the electron transitions should be released as electromagnetic radiation, and based on the energy that they release, the frequency of the energy released will vary. And if you take all of those frequencies and take it as a frequency distribution, what you get is your hydrogen's emission spectrum. Or else you can take the wavelengths of all of the radiation that is released and plot it in a graph as a wavelength distribution, and at that point also what you get is hydrogen's emission spectrum as a wavelength distribution. This is a wavelength distribution, hydrogen emission spectrum. This is the frequency distribution of hydrogen's emission spectrum. Alright everyone, is everything clear to you now? So since some of you are still taking it down, for others you can listen up to a summary of what we have learned so far. Okay, so I will summarize what we have learned so far, otherwise I'll have to just wait until you take this down. So you can take it down peacefully, but I'll just summarize what we have done so far. So basically we learned that hydrogen atoms produce something called emission spectra when hydrogen is provided with energy. So we take a bulb, we fill hydrogen atoms or hydrogen molecules to it, and then we provide it with really high amount of energy. Then what happens? Hydrogen molecules break into hydrogen atoms, and hydrogen atoms will absorb energy. So these are the energy levels of hydrogen atom. We have hydrogen atoms absorbing energy, and the electrons are the ones that are actually doing the absorbing of energy. So when electrons absorb energy, they move on to high energy levels. We say that is in the excited state. Then they will come back down, releasing that energy. When they are coming back down, releasing that energy, they release the energy in few different steps sometimes, or directly they can come down from high energy levels directly to low energy levels. When an electron absorbs energy and moves into high energy level, we call it an excited electron, and we said that it is in an excited state. When it comes back down and stays in the same usual energy level that is always present in, we say it is in the ground state, right? These are things we learned. So based on the electrons transition from like high energy levels to low energy levels, it releases different types of electromagnetic radiation with different wavelength values and frequency values. So some possible electron transitions are given here, and based on the energy that is released, we actually see different radiation listed down here as a frequency distribution, and this is referred to as the emission spectrum of hydrogen. Is that clear? Because they have in the emission spectrum of hydrogen, we have organized all of the different frequency values of the radiation that they have emitted. So this is a frequency distribution of hydrogen's emission spectrum. We can also draw a wavelength distribution of hydrogen's emission spectrum. Is that clear now? That is what we have done so far, right? And once you are done drawing, can even take a look at the 4th page, that there's a table here. Lyman, Balmer, Paschen, bracket series, you can see based on the electron transitions, they have different series within this particular hydrogen emission spectrum. And you can also see they have started with the final, now in the first column they say NF. NF means what is the final energy level that the electron is falling into when producing this particular series. When it comes to Lyman series, electrons fall from high energy levels always to the first energy level. When it comes to Balmer series, electrons fall from high energy levels always to the second energy level. Paschen from higher to third. Bracket from higher to fourth, and then Fund from higher to fifth, right? So those are things that you should remember. Paschen, bracket, Fund. That is the order. Lyman, Balmer, Paschen, bracket, Fund, right? So Paschen series, bracket series, Fund series, those are usually falling into IR region of the electromagnetic spectrum. Balmer series falls into visible region. Out of the entire hydrogen's emission spectrum, this is the only series we can see, right? Others we can't see, but we can measure their frequency values and or wavelength values and draw this, but we can't see it. Is that clear? And then what do you call it? Lyman falls into UV. Is that clear? But students, now we can see, I'm sorry, I actually forgot to draw this also. So this is H alpha, this is H beta, this is H gamma and H delta. So there are other electron transitions as well. This one I have drawn, but there are other few electron transitions that can take place. Those ones are falling onto ultraviolet region, because this is violet. Anything above that is ultraviolet. Is that clear? If you can, please write next to each of these, write the colors as well. This is red, this is blue, sorry, not blue, there is green, this is blue, and this is violet. Write those colors as well. I have drawn those colors earlier, but it's better to write them down like so. The BCS series is actually the Balmer series, has a lot of information in it. Is everyone done drawing this? Shall we take down a small note? Shall we take down a small note? Right? I'll give you a break after that. Okay? So take a small note down. You can write under this. First one to write is, first point, each spectral line indicates an energy gap, between two energy levels, Then write the second point. The gap between two spectral lines, in a frequency distribution of hydrogen's emission spectrum indicates an energy gap between two adjacent energy levels. right? Third point, you can write under that please write this, E equals h nu. You can write delta E equals h delta nu, just to say that this is the gap between two adjacent spectral lines. This is energy gap between two adjacent energy levels. H is the Planck constant. I'm just trying to say that delta E represents the energy gap between two adjacent energy levels, and delta nu represents the frequency gap here. So frequency gap is proportional to the energy gap. Is that clear? That's what I'm trying to indicate here. You can further assist, we can further assist by saying that this is, if you want only you can take this down. This is a frequency gap. You can say that this is the relevant energy gap, right? Hopefully it helps, but students, I think, who are joining online probably can't see. So this is delta nu, and this what I have written is delta E. Done? Can I move on? Right. As the third point, right? As we move away from the nucleus, energy gaps between energy levels, energy gaps between adjacent energy levels decrease. As we move away from the nucleus, energy gaps between adjacent energy levels decrease. This is the reason for the gaps between spectral lines, decrease within a given series. This is the reason the gaps between spectral lines decrease within a given series. Because this reason is usually asked. They ask you why this is happening. So you have to say, the gaps between spectral lines decrease because the gaps between energy levels decrease as you move away from the nucleus. That is the reason. Clear? Right. The final thing that I still haven't explained to you is this. I'm sorry students, I can't, I'll explain this part and give you the note and then give you the break because I can't suddenly stop here. Maybe I can. Yeah, we'll stop, right? I can, right? We'll stop. And then because I don't want to rush, because if I start to explain this, it'll take another 15 minutes. I will feel rushed doing that. So we'll stop here. There is a note associated to this diagram, so I'll leave the diagram here, take a 15-minute break and be here by 5 o'clock, right? Be here by 5 o'clock. Okay, so the next part that I want to explain is this. When it comes to this series that I drew, I actually showed some gaps between certain spectral lines. You should be able to figure it out yourselves by now. What did I try to show you here? That this particular energy gap, we'll take Paschen series. Paschen series, the very first spectral line that we have over here has the lowest amount of energy, right? So Paschen series is a series that is produced when electrons from higher energy levels fall to the third energy level. So the smallest gap could exist when electron from fourth energy level falls to third energy level, right? There can't be any small energy value than that when it comes to that particular series. Why? Paschen series means the energy changes that is observed, or partial series basically has wavelengths that are represented the electron transitions from higher energy levels to the third energy level. The simplest electron transition that can take place is from the fourth to third in that series, right? So this has the smallest amount of energy. This line corresponds to, or this energy transition corresponds to this line, okay? So, and the second line corresponds to this electron transition. And if you take the first spectral line and the second spectral line, the gap between them, the frequency gap between them corresponds to the energy gap over here. Is that clear? But this same energy gap is seen here as well as here. Do you see? Now this energy gap could be explained through the H beta electron transition and H gamma electron transition. I'll give you the name separately. So that means the second and the third lines that I've drawn over here when you're talking about Balmer series. So second electron transition and the third electron transition, that is represented by this second line of Balmer series and the third line of Balmer series. Is that clear? So that would mean, students, when you're drawing the spectrums as well, this delta or this particular gap of frequency should be the same over here. So the gap between these two lines and the gap between these two lines as well as the gap between these two lines should be the same. Why? Because those frequency differences correspond to the energy gap between the fourth and the fifth energy levels. So fourth and the fifth energy level gap doesn't change when you're moving from one series to the other. So the fourth and fifth energy level gap remains the same. But we can see this fourth and fifth energy level gap can be observed as a frequency gap in every series that I have drawn here. But in certain series you don't see it. But in this particular three series we can very clearly see them. Is that understood? Right? So therefore we can take down a small note. You can write we'll take a small one more other sentence. You can write in different series. Sorry? Energy gap between?
The Y is smaller than X in the graph, but the spectrum Y is larger than X.
Bear with me a second. Yes, I have drawn the wrong Y here. Sorry about that. See, the Y is drawn in the wrong location. Okay. So Y should be drawn we can actually remedy that situation another way as well. Shall we now, here we can keep the y's, no problem. Keep the y as it was, right? I have drawn the y in the wrong location, but keep the y here in the same place. We'll change this y, right? Now it makes sense. Okay, thank you for pointing it out. That is correct. Right. Okay, so right, in every in different series of hydrogen emission spectrum, we'll start the sentence again. In different series of hydrogen emission spectrum, similar gaps between spectral lines can be seen. In different series of hydrogen emission spectrum, similar gaps between certain series can be seen. Similar gaps between spectral lines in certain series can be seen. Similar gaps between spectral lines in certain series can be seen. And a list of those gaps are given below. So you can see when it comes to Paschen series, first and second line gap is equal to the second and the third line gap in Balmer series, and the third and the fourth line gap in Lyman series. So this is like a trend. Now if we can actually move this further towards the Brackett and Fun series, so that means Bracken's first and second lines gap will be equal to Paschen's second and third line gaps, Balmer's third and fourth, Lyman's fourth and fifth. Is that clear? So you can extend it, but we don't talk all that much about Paschen and we don't talk all that much about Brackett and Fund. That's why we don't talk about that too much here. But keep in mind that usually they can ask questions about what are the similar gaps that are seen in each of these series. So you should be able to quickly remember this and figure it out, or else you can draw a small sketch and figure it out as well. Because drawing that sketch, although now you might think it's very complicated, no, but you can think about it in your heads and draw. You can draw when it comes to Paschen series, electrons are transitioning from higher energy levels to third energy levels. So you can quickly draw this, you can sketch it in a piece of paper. And Balmer series, from higher energy levels to other second energy level, you can quickly sketch this. So you can see the energy gaps where they are similar to one another. It's not going to be that difficult. But if you can remember this table, it will be much easier. It will be much easier. You don't have to draw that if you remember this, you don't have to particularly draw that. Is that clear? Right. So now, by now we have discussed a lot of details about emission spectra of hydrogen, and emission spectra of hydrogen was explained this particular way through a scientist known as Niels Bohr. He was actually able to show the presence of energy levels within the atom with the use of this model, right? So he explained the hydrogen's emission spectrum using the information that I actually gave out to you. And in your paper, they usually ask a lot about the frequency distribution of hydrogen emission spectrum. So you should be quite thorough with the current knowledge that I have given to you. Apart from that, usually this Balmer series or the visible light region of the hydrogen spectrum is also huge interest to us. They usually ask you about these 4 lines. They are asking about the colors. So the one with the lowest frequency is red, and then green, sometimes referred to as blue-green, but we just say it is a green spectral line. Then we have blue spectral line, and then violet. Now students, as I mentioned earlier, we have actually given each of these spectral lines names. For any other series, we haven't given any names for any of the spectral lines, but for this we have given names. So the very first line, or the red color wavelength, we have given H alpha, and the second one is H beta, H gamma, and H delta, right? So these are the ones that are present within the visible light region. Now imagine this electron transition corresponds to H alpha line that we see in the spectrum here. This particular electron transition corresponds to H beta, H gamma, and H delta. So by this point we have finished talking about the visible light region of the Balmer series. The other electron transitions that are coming from higher energy levels have more energy than the violet light. More energy than violet. So more than violet means what? Where does the radiation fall into? Is it within the visible light region, or more than violet means what? Ultraviolet, UV. So therefore students, these final lines that are present in Balmer series is said to be falling into the UV region category. Is it clear? So we don't see a color there because you can't see UV light. Is it understood? In the sense, you don't see a color for UV light, right? So therefore this last final lines that are drawn very close to one another is falling onto UV region. So Balmer series is a series that contains mostly visible and tiny amount of UV spectral lines. Is that understood? So if someone says Balmer is entirely visible light radiation only, it is wrong. Is that clear? Right? So that is a tricky question that someone can ask. Paschen series and Brackett series, they fall into IR spectrum category. Lyman falls into UV. Now these are things that are asked usually in other past papers as well. So shall we move on to some questions from here, because now it is time for us to have a look at a couple of questions. Now we have observed basic concepts of emission spectrum. We have to now move on to the next part, that is doing some questions related to this. So turn to, bear with me, turn to page number 35. Turn to page number 35, the 6th question. Oh, sorry. We'll start with 7th question. 6th question is directly about this part only, but I want to see how you answer the 7th question as well. So attempt the 7th question first, and then we'll move on to the 6th. Did you write this down? You wrote it down, right? I hope you remember these things. Shouldn't be that difficult. Students who are joining in, today, like join for the first time today, don't worry, we'll explain these things. Which school are you from? Clayton College. Sorry, is it close by? Alright. Have you finished this part in school? Not yet. This part? This is new initial bits. Are you starting there now? Is there anything that you didn't understand here? Correct. What about you? What is your school? Clayton. Both are students. Clayton. Alright. You haven't done these things in school? Are they just starting up? Like, school just started, or?
You mean the year they started?
Yeah? No, I'm asking whether, like, you said you haven't done these parts in school yet, right?
No, like we don't go to school like everything is sponsoring.
Is that the case? Okay. Alright. I understand. Is there anyone who's done with those questions? No, done. Right, I think that's about enough time for this question. This is not a very difficult one. Let's see. When a beam of particles falls on a thin gold plate, most of the beam of alpha particles most of the alpha particles pass undeflected through the plate. The first one, the gold plate contains spaces which are large compared to the size of alpha particles. Second one, gold plate is non-continuous. The third one, path of the particles is always linear. So, for example, when we did Rutherford's gold foil experiment, we observed if you take a thin gold plate, thin gold foil, and shoot alpha particles to it, the alpha particles pass straight through the plate, not plate actually, straight through the foil, right? Majority of the time, it passed easily through the gold foil. And based on this, Rutherford made a conclusion. What was the conclusion? most of the atom's space is empty. Atom is mostly empty space, he said, right? So basically the first statement agrees with that. The gold plate contains spaces which are large compared to the size of the alpha particles, which is true. Atoms are mostly empty space. So here basically the similar meaning to that is given here through this statement. So it is justifying why the alpha particles moved straight through the gold foil. Is that understood? The first statement is correct. And they say the second one, gold plate is non-continuous. That means there are holes in it. Like, imagine if I take this page and punch a few holes in it, then it is not continuous, non-continuous, right? So is that the case with the gold plate that we used? No, gold foil in the Rutherford experiment was continuous gold foil, right? But still particles moved straight through it. So the second one is definitely wrong. That is a X. And they say if keep the appropriate box empty if you are unable to evaluate the validity of the explanation. So the third one is something like that. The path of alpha particles is always linear. So the path that are shot, the alpha particles that are shot out of this radioactive element was moving linearly. That is true. They were moving in a straight line. But does that directly explain this, or is it not explaining it? So that is very difficult to determine, because if the alpha particles were not traveling in a straight line, we can't determine whether the spaces between the gold atoms were mainly empty, right? If they were traveling like in a weird way, we can't determine it. We can't properly determine it, right? So therefore, alpha particles traveling in a linear manner is important, but it doesn't completely explain this as well, but it is important for the explanation as well. So we can't properly determine whether this is completely explaining this statement. So therefore we can leave that box empty. So they say if you are unable to evaluate the validity of the explanation, you can leave it blank. You can leave that blank. The B one, a pedal wheel placed in the path of the cathode rays rotates. So cathode rays are negatively charged. Does that have anything to do with the pedal wheel experiment that we did in cathode ray? What was the main point of doing a pedal wheel experiment using cathode ray? Particle-like properties. We said these cathode rays had momentum, or had a mass as well as a velocity. That means they had some kinetic energy which was transferred to the pedal wheel as they collide with the pedal wheel. So that kinetic energy was given to the pedal wheel, which made the pedal wheel move. So therefore it being negatively charged has nothing to do with this. So therefore it is not explaining the pedal wheel experiment clearly. And then the second one, cathode rays have particle-like properties. True. Yes, that is correct. Material of the pedal wheel is continuous. Again, this is not clearly explaining it directly, so therefore you can put a cross in that place. Right? And then we move on to the C1. The electronic emission of spectrum of hydrogen consists of several series of lines. In each series, the separation between lines decreases as the frequency increases, meaning the gaps between the lines decreases as the frequency increases. The first statement, there are definitive energy levels for electrons in hydrogen atoms. So yes, that is correct, that is true, but is it explaining this? No, but you can't properly say no also. It's a bit difficult to determine the validity. We'll for the time being keep it aside. And then the next one, the energy corresponding to each line in spectrum is equal to the energy of an electronic energy level. Is that true? Each spectral line corresponds to the energy of an energy level. Is that the case? each line corresponds to energy gap between two energy levels, not to the energy of a given energy level itself. Is that clear? So for example, this first line doesn't talk to us about the energy of this energy level. It talks to us about the energy gap between the two energy levels. Is that clear? So this statement says it corresponds to energy levels value, energy value. That is wrong. So that one is clearly a wrong statement. So it doesn't explain. The second one, the energy of the electron decreases with increasing radius of the atomic shell. The energy of the electron decreases with increasing radius of the atomic shell. So basically, students, if the electron moves further away from the nucleus, they say energy of the electron decreases with increasing radius. Meaning, if electrons are further away from the nucleus, this statement say electrons' energy is decreased. Is that the case? I explained it to you using a classroom setup, right? Like, are the students way at the back in a, like, let's say a really big hall class, more attentive to the lesson than the ones that are here? No, right? So just like that, when it comes to electrons also, the further they move away from the nucleus, the greater the energy they have. So this statement says the opposite of that, right? Radius means the distance between the nucleus and the outermost energy level. We sometimes call it a shell, but energy level, the great, like, distance between the nucleus and the energy level, as it increases, the energy of the electron also increases. So the third statement is wrong. The fourth statement, however, at least one should be somewhat correct, right? So let's see if the fourth one is correct. The energy difference between successive levels, decreases as the energy of the electronic level increases. Absolutely. As the energy of the electronic levels or energy of the electronic energy levels increases, you can see energy gap between them decreases. So that is what the fourth one says, and that is the reason for the gaps between the spectral lines to decrease as well. I have given that note to you, right? So the gaps between spectral lines decrease as the energy gap between energy levels decrease. So the fourth one is correct. The first one we can say we can't determine correctly, because that statement is true, but it is not explaining the situation correctly. That statement is true, but it is not properly explained, so we'll leave it blank. Is that understood now? Clear? Right. So move to question number 6 now. There is a small additional line to be drawn here. Do you see there's n equals 1, n equals 2, n equals 3 is missing. That line has gone missing. Please draw that. Right? You can draw n equals 3 line and do the question. Now this is an actual exam question. Please keep in mind, students, they have given only the lines that you need to answer this question. So you have to utilize the lines fully. So before you start answering, think of a strategy to use these lines fully. Right? So now start the question. Anyone who's done? This is a simple part. Anyone who's done with this part? There is another couple of questions on the other side. I hope you have done those parts as well. Shall we attempt this part? Right? Finish it off? Right. So now, in a question like this, now first of all, let's read the question. Figure 1 shows the first 5 electronic energy levels of a hydrogen atom. Figure 2 shows 6 lines of the emission electronic spectrum of the hydrogen atom. So now we have the first 5 energy levels and the emission spectrum. Have they stated whether this is the frequency distribution or the wavelength distribution of the emission spectrum? They have not, right? So then how do you figure it out whether it is like the frequency distribution or the wavelength distribution? There are telltale signs, students. You should be able to figure them out now. Now, always, no matter what spectrum it is, whether it is emission spectrum
or the wavelength related emission spectrum, whether it's frequency distribution of the emission spectrum or the wavelength distribution of the emission spectrum, the gaps between spectral lines are usually decreasing. The gaps between spectral lines within a series usually decrease towards the direction where the frequency is increasing. That is, in both wavelength as well as frequency distribution emission spectrums is a common thing. That is like the only similarity that you would find, right? So that is, again let me repeat, this is the direction where frequency is increasing. How do I know that frequency is increasing towards this direction? Because the gaps between spectral lines within a series decrease in that direction, right? Here also gap between spectral line decrease in that direction, meaning what? That is the direction where the frequency is increasing, right? So we know in the frequency distribution of emission spectra, we observed in the same direction the length of the series also increase. That was one of the points that I gave you. In the same direction where the frequency is increasing, the length of the spectra increases. When you are moving from Paschen to Balmer to Lyman, the length of the series increased. But now turn to page number 5, I think, and see how the wavelength distribution of emission spectra, how their lengths change. So if you turn to page number, was it page number 5? Bear with me. Yes, page number 5. So if you take a look at that, you can see wavelength is increasing to this direction. So we can definitely say frequency is increasing the other direction. And another telltale sign is again what? The gaps between the spectral lines within a series decreases towards the right hand side. So therefore students, when it comes to, actually in your case it is decreasing towards the left hand side. So basically towards the left hand side it decreases. So that means frequency is increasing towards this side. So you can see the length of the series decreases towards the increasing direction of frequency. Is that understood? That is for wavelength distributions. We rarely talk about those. For frequency distributions, it's very easy to remember. So frequency is easy to remember because of these reasons. Lines, so gaps between lines decrease within a series to the same direction where the frequency is increasing, and to the same direction the length of the series are also increasing. Is that clear? And gaps between the series also increasing in size to the same direction. So that's why when I was giving you the note, I write in the direction where the frequency is increasing, semicolon, and then give you the 3 points. Can you remember that? Right? So this is definitely telling us this is a frequency distribution of our hydrogen emission spectra. That means in this direction frequency is increasing. That means this particular line should be representing a very small energy gap, right? But then also they say that these two are adjacent to one another, and we have to utilize this entire thing, right? So that means, imagine you have to draw a line from here to here. That means this would be Lyman, and that would mean this is Balmer, right? So since if you think this is not Lyman and you don't draw anything here, we leave majority of this thing empty, and then we will not have enough space to draw 3 lines in the next part. Like for example, imagine you started from here, 1, 2, 3, and then if your next one should be ending up in the third energy level, right? So then 1, 2, the third one you don't have another energy level to draw. Is that clear? So you are running out of energy levels. Make sure that you think before you start drawing. So this one is a lower energy series, this one is a higher energy series. So we can think of the highest energy one, which is Lyman. So we can think this is Lyman, this is Balmer. So if this is Lyman, this particular line would be produced when electrons transition from second energy level to the first energy level. and then B2 will be formed when electrons transition from third energy level to the first, and this one will be formed when it transitions from fourth energy level to the first. Is that clear? And since this is the adjacent one to Lyman, that means this particular series has its electrons transitioning from a higher energy level to the second energy level. That means we are stopping at the second energy level here. So that means this is the line that has the lowest frequency. That means electron transition from third to second would be producing this line. And the next one is from fourth to second, and finally from fifth to second. Is that clear? If you started any other way, you would not have enough lines to represent, actually enough energy levels to represent these frequency values. Is it understood? So that's why I said think. It's a bit of a thinking game. So if you thought this was Paschen and Paschen and Balmer, you would not have enough lines to represent Paschen, because Paschen means what? Energy transition, so electron transition from high energy level to the third, right? So high energy levels to the third, there are only two transitions you can show. You will not have another line to show, or another energy level to show the third line here. You are running out of energy levels. Is that understood? That's why we choose Balmer here and Lyman here, not Paschen and Balmer. Is that understood now? Right. One final question, but this question has been extremely simplified for you due to a small printing error, students. So when I was sending this question to the printers, actually for the typist, I roughly did this question and I noted down the energy transitions, and she has drawn the lines as well and sent to the printers. So basically this question is partially answered for you, right? You have to draw these lines. I have already drawn it for you. So that was a mistake. So do this question. When it comes to page number 38, we have question number 10. Don't do the A part because you are still not equipped to do the A part. Do the B part. Do the B part. Don't do the D part as well or the C part. Just do the B part. I'm sorry, I think I missed out on a couple of questions, right? On the sixth one. So the sixth one says, draw 6 arrows between energy levels in figure 1, and then electronic transitions should be shown. That is what we have done here. So this is the part 1 of the question. Part 2 of the previous question is, clearly label the in figure 1 these arrows appropriately as A1, A2, A3 and B1, B2 and B3. So we are write A1, A2, A3. This is B1, B2, B3. Strike off the inappropriate word within the bracket in the following sentence. The frequencies of spectral lines increase/decrease from A to B3, A1 to B3. So from A1 to B3, frequencies of spectral lines increase or decrease, students? Increase. So we are going to cancel off decrease part, because we want to say it is increasing. Right. So now we'll finish off the last question. That is quite easy. Do this one, please. Done? Simple one. So let's discuss this. So that is such a simple question. So they are asking us, indicate with arrows the electronic transition that could occur between the above energy levels and which are responsible for emission lines in A, the infrared region, B, visible light region, and C, ultraviolet region. So now students, they have in this question given you only 4 energy levels, right? This is the question, right? This is energy level 1, right? This is energy level 1, energy level 2, energy level 3 and energy level 4. So I would draw this a bit up like so, right? So now basically they are asking you to show A, infrared region electron transitions that can take place, then visible light, then UV. Basically, students, they are asking you to show electron transitions that fall within Lyman, Balmer and Paschen, right? So we are starting with Paschen because they have said A is infrared, and then B, and then C. So basically, when you read the question, you will get a sense they are asking for IR, visible and UV, meaning IR, one that we can see very close to visible, is Paschen. Actually, bracket is also IR, but you can't properly see that, show that here, because when it comes to bracket, electrons are transferred from high energy levels to the fourth energy level. We are starting with fourth, no, we are ending with fourth here. We can't show high energy level transitions. So, but when it comes to Paschen means high energy level to third energy level electron transitions. So we can show that here. High energy level to third energy level electron transitions. So this is A. We don't have any other IR related electron transitions. We don't have any other energy levels above 4, because for us to show few electron transitions, electrons falling from high energy levels to the third energy level, we have to have few other energy levels here. We don't have any. So this is it. And then we have visible. Visible, of course, visible is like the way that we can quickly figure out. It is high energy levels to second energy level all the time. So that means we can show one transition, two transitions. That's about it. We don't have other energy levels to show the rest of it, right? So this is visible. Sorry. And the next final one would be UV. UV means electron transitions from higher energy levels to the first energy level itself, like so. Is that clear? So therefore, you can show 3 electron transitions in that particular region. So you have to show all of them. They ask you to show all. That means these are the transitions you can show. So this is IR, this is visible, and this is UV. And to go a step further, we can write this is Paschen, this is Balmer. Now these are names of scientists that explained this part of the series. So Paschen explained this part of the series, Balmer explained this part, and Lyman, he would have explained the UV region of the hydrogen emission spectrum. Is that clear? Right, otherwise we don't give them like weird names like this. Not weird, I'm saying we don't give them separate names like this. It is the scientists who have actually explained this part of the hydrogen emission spectrum. So therefore, we have named each of these regions of the hydrogen emission spectrum with their names. Okay, is it understood now? So these type of questions you can expect, and we'll be doing more questions towards the end of the lessons when we are finishing off the lessons. So normally at the end of a unit we will be doing a couple of questions and then a small paper. So we can expect that when we are finishing unit 1, but we are not yet done with unit 1. This is one of the key important parts of unit 1. Hydrogen's emission spectrum. That's a massive part. So after that, we are actually using hydrogen's emission spectrum to talk about, bear with me a second. When it comes to hydrogen's emission spectrum, you will see you can't explain Niels Bohr actually. Niels Bohr used hydrogen emission spectrum to explain energy levels of the hydrogen atom, but you couldn't actually use the same theory to explain emission spectrum of helium, emission spectrum of lithium, or any other element. So Niels Bohr's theory actually failed when it comes to explaining the emission spectrums of any other element. Is that clear? So that didn't necessarily work out. Understood? So therefore we stop at this particular point for today, and we are going to be exploring the other different theories that came later after Niels Bohr's explanation failed there were many other theories that came. Like for example, there was Heisenberg and there was Schrödinger. They were explaining why the Niels Bohr's explanation could not be applied to any other atom. And then eventually Schrödinger, he brought up a theory that we to date also use about hydrogen atoms and other different atoms and how the electrons within atom are actually arranged. The thing that you think, right, you currently think electrons are nicely moving around a nucleus, right? That is not correct. So you are going to learn that it is not correct through Schrödinger's equations. So we come to that next week. If you can, before you come to the class next week, please go through the TUTE all the way up to page number 13, right? So please read through those and then come, because it will be easier for us to explain this new concept about electrons not being in a specific circular motion around the nucleus. That is embedded into your heads, but if you can read through those parts and come, then you will realize, okay, that is not correct. Then you will have a bit of a better idea about how the electron behaves within the atom. Okay, so with that we will conclude today's class, and I will be meeting you again next week. So do any of the questions that you can find on spectroscopy, we will discuss. If you bring any difficult questions, we will discuss it in class. Alright everyone, that will be all for today. I'll see you again next week.